Hello, so today we are doing this problem called permutations, and so the problem says we get a collection of distinct integers and we want to return all possible permutations. So for example, we get 1, 2, 3, and the possible permutations are 1, 2, 3 itself, and then putting 3 first, so before 2, so 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So there is no other arrangement that we can make for these three numbers. These are all of them. And so the goal here is to enumerate all of these possible permutations. So how can we solve this problem? So this here, generating all possible permutations, it's if you look at it, it's generating all possible configurations in something, right? All possible permutations here for some set, which is here, or some space, which is here, the numbers, the set of numbers that we get. So immediately when you have a problem like this with all possible configurations of something, we need to think about backtracking. I have a video that I will link in the description that explains how to solve a general way to solve backtracking problems, and that's what I will be applying next to solve this. Okay, so let's see how we can solve this problem of permutations. And so what essentially the problem says is that we get some numbers, a set of distinct numbers. So for example, what we had is 1, 2, 3, and we want to permute it. And so we can just say we would have some values v1, v2, and then until vn, and we want to permute these numbers. And so what we can notice here is what we need to do is just fix one of the numbers, one number, and so consider it picked, and then permute the rest, right? Which basically means n-1 elements left. Or basically we would have, so, and this basically means is pick v1, or have it fixed, or fix v1, let's call it instead fix v1. Then after that we will have n-1 candidates to pick or not, to pick, right? To pick in whatever order we want, and then append it to that v1, right? Or also we can insert this v1 in any other place, right? But essentially the main idea is that we pick one and then we would have n-1 choices to make. And to pick in and so basically this means that we will have first we have n choice to pick one element, right? And then after that we will have n-1 element to pick, and so we would have n-1. And then when we pick that n-1 element, it can be any of the other remaining elements, because like if we have 1, 2, 3, we can first pick 1 and then permute 2, 3, or we can pick 2 and permute 1, 3, or we can pick 3 and permute 1, 2, right? So we have n choices here, right? But for these 2, 3, for each of these, we have only 2 choices in each, right? So from 3 choices we have, or n choices, after that we have n-1 choices, and then this keeps going, n-2, yeah, until we have only 1 element left. And so this is, we have n factorial, right? So we know that we have n factorial distinct permutations. Now, essentially, now what I said is that we want to apply the generic way of solving backtracking problems that I explained in another video that I will be linking in the description, which is that what we need to do is model the solution in terms of a vector, in terms of a solution vector. And then from there, once we have that, we can just figure out when do we have a solution, and figure out what we need to process the solution, and then figure out at each step for adding to our vector solution what candidates do we have, and then go through these candidates and construct, basically make the move, backtrack, and then make the move. And so just following this template here. And so to do that, let's think about what is our vector solution. So it would be something with some values. These values are the ones we need to figure out. What values do we need to help us solve the problem? So one thing we know is that when we pick an element, we shouldn't pick it again, right? Because if we pick it again, then that's no longer permutation, right? And so that means that the next element to choose can be any element that is not picked yet, right? Can be any element not picked yet. You can see that with, for example, 1, 2, 3. Once I pick one is in my partial solution, which is vector solution A here. If A contains 1, that means I can't pick 1 again. I have to pick 2 or 3. I can't pick 1. If my vector solution so far has, let's say, 1 and 2, the only thing I can pick is 3. I can't pick 2 and 1, right? Because if I pick them, that's no longer a permutation of 1, 2, 3. And so I know that the candidate solution in any step, in any next step, are always candidates are always any element of the remaining that are not in the partial solution. Right? So now I know my candidates. So that means that, I know how to, so I know two things here. I know the candidates and I know my vector solution. I know that my vector solution is just the portion of the permutation that I picked so far, right? And so if I go again to the template that we have, so I know how to construct my candidates because they will be just the elements that I haven't picked yet, right? And I know my vector solution that I'm modeling here. Now, when do I have a solution? Basically, it's a permutation of length n. So I have a solution whenever the length of my vector that contains the permutations so far is equal to the length of the initial set, right? It's equal to n. And so here I have a solution when length of A is equal to the length of the original set. Let's just call it n, right? So now I have this portion. The only portion left to have the template done is the process solution and what are the make move and make move that I will be making. So process solution is, I just want to add to a list so that I can put that final list in order list of permutations. So my process solution would be just having an array that I put the result in. So I would have let's say an output array. And in the process solution, what I would do is just add the vector solution A, because that would contain all the elements picked so far. And since I have the size equal to n, that means I have a permutation. So I can just add that and then backtrack and try to find a better solution. And so now, what would be the making a move and making a move, right? So all I need to do is add the element. So that would be just So that would be just adding the element to the vector solution, right? And that element would be just one of the candidates, right? So that would be C. And then M making the move would be just removing that so that we can add the other possibility, the other candidate, because I have a set of candidates for the next step. So I have a set of candidates for the next step. I add this one and then try to go back and back all the way until I find a permutation. And then once I'm rolling back, I need to remove this so that I can try the next candidate, right? And so M make the move would be just removing the last element that we added to the A, and so that would be pop. And so now I have all the methods that I need to plug into my template solution here, and I can just solve it, right? And so to visualize kind of what this looks like, so basically what we will be doing is just something like this. So we would have the original list, let's say 1, 2, 3. So what will happen is that first we will pick 1, and then the candidates will be 2 and 3, right? And so I will try both 2 and 3. And now once I'm here, the only candidates elements not picked yet are 3, right? Because I already picked 1 and 2. So at this point I already picked 1 and 2, and so the only possibility left is 3. And at this point the only candidates I have are 2 and 3, and so that's why I put them here. And here the only candidate left is 2, and so I pick 2. Here the candidates are, at this point, the candidates are 1, 2, 3, and so I pick one of the two. I already picked 1, and so I already tried 1, and so I backtrack again, and then I try 2, and then 2. I have the candidates possible that are not picked yet are 1 and 3, and so here basically when I reach here, one thing that I should mention is that when I reach the leaf, I would have here 1, 2, 3 as the permutation, and so this length is equal to n, and so I will process the solution. And then here, once I arrive here, so this is actually the solution. So let's just put it in another number. So that's 1, 2, 3. And here, since the length now is n, I have the permutation 1, 3, 2. So I backtrack. I already did 3. I backtrack, basically doing pop and removing 3 from the solution vector, and then I'm at 1, and then I already did that, and so I pop 1 again, and now I have empty, and now I add 2 using the make move here, and then adding 2, now I would have 2 in my vector solution, and then I would after that have 2 choices, 1 and 3. So those I will try first 1, and then when I'm at 1, I have in my vector solution 1 and 2, and after 1 the possible candidates I have are just 3, and so I pick 3, and now my vector solution is 1. Sorry, it's I made a mistake here. My vector solution is 2, 1. So now my vector solution is 2, 1. I pick 3. My vector solution is 2, 1, 3, and my list of candidates is empty now, and I go to check if I have a solution. The length is n, so I have a solution, and so I add that to the output, and I continue doing this using this backtracking method here. And so now that we know how to do this, let's code it up and see what it looks like. Okay, so now that we know the methods that we need to plug into our template method for solving backtracking problems, we can just start coding it. And so the template was to have to have a backtracking function that gets the input, that gets the vector solution that is initially empty, k, which is where we are in the vector solution, and then the input array, which is just the, or whatever input value, and I'm just going to pass the entire original list here. So I'm going to call that here with backtrack, and the vector solution, which is initially empty, and then we are initially at position 0, and we pass the initial input, which is just nums. And so for this template, I'm just going to write the template, right, which is checking if we have a solution, and passing to that, I would need to pass n, which is the length of the input array. And then if that is a solution, I can just process the solution and return. Otherwise, or let's just do else. Otherwise, I construct the candidates. So this is just the template so far. No new code yet for this problem. This is what we will be writing for all of the problems that we, backtracking problems that we will be solving using this method, basically using this template. And so we would have the input array, and then now we need to do our specific things. But here we need to make a move where we would do our specific code for this problem, and then call backtrack. This is part of the template here. We would call backtrack on the next. Sorry, this is construct candidates for k, and then backtrack, go to the next position. And remember, it's a DFS, so it goes all the way down until we have a solution. And then we pass the input array. That's what the parameter that backtrack requires. And then after that, we need to make the move. And pretty much that's just the template. Now we will define our own functions. So one of the functions that we needed, which was the defining the solution. This is the one that is specific to this problem. And so we will get k, and then we will get n. So we said that we just need to check that the length of the solution so far we have is equal to n, which means we have all the numbers picked. And then we need to process the solution, right? So processing the solution means just adding it to the list of results that we have. So we would have the output here that we will return at the end, which is the list of all permutations that we have here. And then from there, here in the process solution, we just need to add that, right? And so output dot append. So process solution will get past the solution we have, that we determined that it is a solution, and so we need to add it. But just be careful here, because if we just add the reference to it, it will get changed maybe later in the make move and will affect the solution that we've already placed. So to just prevent that, we need to copy, and now we need to construct the candidates, right? And so this is also specific to our problem, and what we said in the explanation is that the candidates are all the elements that are not yet picked, all the elements that are not yet in the partial solution, which is A. And so to determine these, I'm just going to say that the elements that we picked so far, I'm just going to have a map for these, and then I'm going to go through. So we are at position K, right? And so to find all the elements in K so far, in A so far, I'm just going to go through all of them and say that all those that are in A, in the partial solution, which are the values until K, those are in the permutation that we have so far. And so I'm just going to set them to true. And now the candidates are all those that are not in that permutation list, right? And so I can just say in my original array, anything that is in it that is not yet picked, that's one of the possible candidates, right? And so that means anything that is not in, that's one of the possible candidates. And so I append that, and I can just return candidates. And so now I did the methods that are specific here to this problem. There is the make move and the make move. So I have to add the candidates to my partial solution, the value that I'm picking. And then I have to pop it, right? Because as I said, when I'm traversing and I add 1, 2, 3, and I have that as a solution, and I want to backtrack, I want to remove 3 so that I can have just 1, 2, and then backtrack again and just have 1 and try 3, right? And so these are the 2 also specific to this solution, but the template is still the same, and the way of thinking about the solution is still the same. So yeah, let's just run this and see if it works. Okay, looks like. Okay, so that solution passes. Now, in terms of time complexity here, what is the time complexity? So we know that we are doing, we said earlier that we have n factorial permutations, right? So we know that just to have a correct result output that contains everything that should be in the solution, we need at least n factorial, both in space, because we need to save these in the output, right? So we know that at least our space complexity would be O of n factorial, and since the other things that we are saving in candidates and the other space that we are using is in permutation and candidates, those won't be more than the O of n factorial because they are a smaller subset of the number of elements we have. So they are always less than or equal to n. So we know that our space complexity is O of n factorial. Now how about the time complexity? So again, since we have to generate n factorial permutations, so that means that a solution would be called at least O of n factorial time. So we know that at least it's O of n. So this is the lower bound. But is that our time complexity? Actually, no, because we have this for loop here that for the first element gives us n minus 1 candidates. For the second element gives us n minus 2 elements. And we are, so basically this here at most, each time it's at most n, right? And we are calling all of this n factorial times. And so this is bound by and upper bound is yeah. And so we know that this is our time complexity and this is our space complexity for this solution. So now that we did it with this, maybe you will think this is a little bit too much or a little bit too hard, but I'm doing it explicitly this way so that because other complicated problems of backtracking that are not as simple as permutation, the intuition may not come easier, but having this framework of a template for solving the problem makes it a little bit easier to direct your thinking to what to find out to solve the problem. Like you just need to find out what is the solution, what is the process solution, what are the candidates at each step, right? So next what I will be doing is just trying to make this code simpler, yeah, basically, yeah. Okay, so now let's simplify this. So is solution, we can just check. We don't need a function for that. We can just do this here. So something like this. And for process solution, we need to define n, right? So let's just define n here as the length of the numbers. And process solution is just adding to the output. So that also we can just put it here. And we no longer need these two. Construct candidates here. Essentially what I'm doing for all of this is just finding the numbers that are not yet added to the permutation. And so what I can do instead of that is just go through all the numbers. So that would mean the range of n. And then to not pick element that I already picked, I can check if the number is in A, which basically means it's already picked in the permutation. I can just ignore it, right? So that would mean this here would replace the construct candidate thing, because all I'm doing in all of this is just checking if it's already in the permutation. I'm skipping it but if it's not in it, I'm adding it to the list of candidates. And so here I go through all of them. If it's already picked, I skip it. Otherwise, it's a candidate, and so I use it. And so C here became numbers names at I, and that's pretty much it. And so I can remove this entire thing here. And here we just need to pass A. We no longer need this input array thing. And that's pretty much it. So you can see after we solved it using that template, we can simplify the solution a lot. So we need just original one in the position. Another thing you may notice here is that we actually don't need k, because we are using we could have done k here equal to n, but we are already using the length here of a, so we can just remove this k also. Right. And with that, we should be good. Just need to remove this. And that solution passes. And so first thinking in terms of the general template, solving it that way, and then after that we can simplify. Yeah, so that's it for this this way of solving it. Next I will be trying to solve it in a different way. Yeah. Okay, so now that we've seen how to solve this problem using backtracking, which is kind of doing DFS, now let's see how we can solve it using something that is similar to BFS, actually. Because the way we are going to think about this is basically to permute n numbers. So let's say we want to permute n numbers, right? At position k, right? So let's say at the fourth position, or the fourth element we are going to pick, we can just pick the all permutations of the first k-1 numbers and insert k, insert basically the number at position k in all possible positions of these permutations. Let's call these p. Let's call this pk-1 of pk-1. So let's take an example to understand this. So first, at the start, we would start out with the result that contains only the empty list, right? Because that's when n equal to 0, that's what we have, right? And then what we will be doing is first, we will have the first number. Let's say I'm going to permute 1, 2, 3, right? So first, for 1, I will take all the permutations of the first k-1, which is just an empty list, and then add 1 in all possible positions. The only possible position is the first position, and so I would end up with this. And so now my res becomes just this. The next step would be to add 2, right? The next step is to add 2, right? So I'm going like this. So for 2, I have to insert it in all possible position of pk-1. This is pk-1. All possible positions are before 1 and after 1. And so I would have 1, 2, inserting it after 1, and then the other possible position is before 1, and so 2, 1. And so my res at this point would become 1, 2, and 2, 1. The next step would be for 3, right? And so again, I need to insert it in all possible positions of pk-1, which is this one. And so all possible positions are to add it in position 0, right? And so first I can add it to position 0, so that would mean I would have 3, 1, 2. Then I can add it in position 1, and so I would have 1, 3, 2. And then I can add it in the last position for this one. I'm still at this one, and so that would be 1, 2, 3. And then I go to this next one, and then I add it to all possible positions again, so that 3, 2, 1, 2, 3, 1, and at the last position, which would be adding it to like this. So you can see it's kind of level by level. So first I do the first level, and then I insert 2 in all possible positions to construct the second level, and then I add 3 in all possible positions to construct the third level. And so you can see this is kind of BFS here. And so to implement this, basically what I need to do is to have first my initial result list, right, which I said it's initialized as empty, and then I go through each one, right. Here I want to 1 and then 2 and 3, and so I say for I, and just I need the number, and so I'm just going to enumerate. And now my new level list, so that's my new result, right, the one that I'm going to change here, and so that gets initialized to just an empty list, right, and then I'm going to add these values. And so what I need to do is insert it basically in all possible positions, right. And so what are all the possible positions? Let's call them J. So those are just, since I'm at position I, so when I'm at position 0, all possible positions are before and after, right? So it's 0 and 1. And then at position 1, all possible solutions are at position 0, 1, and 2. So it's I plus 1, right? And now I pick all the, so I pick for each permutation of the previous config of the previous one, which is pk minus 1, I need to try all possible positions. And so I need to go through all the previous permutations, which are just previous res in res, and then I need to try to add to each position. So this loop, I could have made this loop first, but it doesn't matter, both will yield the same thing. And so my new result would have, basically would have what I've done here, which is in this one, try every possible position, try inserting the new element. And so that would mean I'm going to append, so inserting at position at position J here means just I'm going to take the previous res up until just before the value J at position J, and then I'm going to add my new value, which is the number here at position I. So that's 3 in this case, for example. And then I'm going to add to the rest, right, which is J until the end. And so this means basically I'm inserting at position J. So this portion here is just insert at position J. Sorry. And then after that, since after each level I need to replace my res with the new res, right? That's what I did here, so that in the next iteration I can insert in all possible positions of the previous res. And so that would mean here what I need to do is after doing it for all positions, my res would become the new res that I just filled up. And then at the end, I can just return the result. So you can see, instead of going all the way down and filling the permutation, I'm filling them level by level. And so let's code this up and see if it passes our test cases. Okay, so now let's code that BFS kind of solution there. So we had first res empty list, and then just going through the numbers where each of them represent a different level, and so like this. And then we have the new res, which is the new level content or the new level permutations. And so we'll try to insert the element at each position in each permutation of the previous level. And so that would mean here we would take for each previous permutation, we will insert at position J and then add that to the new result. And so that would mean just take the previous result just before J, add the number, and then after J, and then after that here for the next level we want the result or the previous permutations to be the ones we just computed, and then at the end we can just return the final result that contains the permutations of length n, which n is just the length of the numbers that we have. And so let's run this. So this is so this needs to be a list so that the concatenation can work. Okay, so I'll submit. Okay, so that solution passes. So to recap, what we saw here is first starting from the backtracking, like just identifying that this is a backtracking problem, applying the general template methods for solving backtracking problems, simplifying that, the code for that once we have the code working, simplified, and then after that, since we know that's a DFS solution, there is probably a BFS solution, and so we tried to think about one, and this is the BFS solution. Yeah, so that's it for this problem. Thanks for watching, and see you next time.